All right. Good afternoon, everyone. Welcome to the DA session. We've got a number of exciting talks, starting with Avichal, giving a background on some DA and HAFS.
Yeah, 15 minutes. All right. I'll take like less than that. All right. Good afternoon. Thanks, Jason. So we'll be talking about some very exciting and potentially revolutionary data assimilation developments in context of HAFS in this session. I've been looking forward to this session since my talk yesterday morning. And I'm very happy that we have a very healthy attendee delegation of data assimilation experts here. Very happy to see that they could attend HFIP and contribute to this session. Okay. All right. But before we get started, the objective of my presentation here is to lay the groundwork, give everybody kind of a baseline as to where we are right now, how DA is working in our operational version of HAFS, what other changes we have made very, very recently, and which are available to us. Next. Oh, I can. It doesn't work. Okay. Next slide, please. So here's a brief outline. So I was saying, I'm going to start with the current status of HAFS v1 DA. Talk about v1.1D. We already heard about this earlier today, and how this is probably leading us towards version 2 of our DA, though it's not final yet. And then talk about some near-term plan beyond V2, so I'm calling them V2 plus, and also some long-term plans, which I'm calling V3 plus. Next slide, please. So here we are in terms of the current status. There are a lot of utilities which are needed to do proper DA and BI in context of hurricanes. And these are utilities available to us. These are UFS utilities, and they're also UFS-based infrastructure utils, which we use, whether those are dealing with interpolation and remapping, merging domains, providing interfaces to different data assimilation methods, making sure that we have a consistent vortex from cycle to cycle. Another DA technique called FGAT is also available to us. We had to work last year quite a bit, and we got good help from EIB and others within UFS to extend the right grid component, make it work for multiple domains, meaning both for the parent and the nest, and also have FMS support. And GFDL and AOML folks played a big role in this for telescopic nests as well as multiple nests. In terms of our data assimilation technique, we're using a 6RD DA cycling for the nested domain. We use a ±3R FGAT window. We're using 4D NVAR with GDAS ensembles. We are leveraging, of course, all observations being used by GFS, GDAS. And then for the near storm or vortex level, we are using additional observations in our core, things like TDR, NextRad, wherever it's available. We do dropson drift corrections, like we used to do with HWARF, METAR, OBS, as well as high resolution GOES 16 AMBs. Next slide, please. And one good example, and this innovation comes to us from Oklahoma University, thanks to Shu Guang and her group, who tested uses of 4D NVAR in HAFS v1. This was, I think, almost a year, well, maybe 9-10 months ago. And we immediately saw an impact on the results for HAFS v1, and we were happy to include this in HAFS v1. Next slide, please. So in terms of the workflow, Of course, it's quite complex. As I took the slide from Jing's earlier presentation, but some of the available DA options as per this workflow, which is a modular workflow, which is how we're designing things in UFS. We can turn on and off VI, turn on and off FGAT. We have access to multiple DA methods, ranging from 3D VAR, 3D NVAR, 4D NVAR, ENKF, as well as hybrid ENKF. We can do 3D NVAR or 4D NVAR. We can do with GDAS ensembles as well as with HAFS-based ensembles, a little bit more on that. Domain, we can deal with storm-based domains as well as self-cycled static domains. And observations, we have access to conventional obs, recon-based obs, satellite-derived winds, satellite-based radiances, as well as TC vitals. Next slide, please. So this is where, in context of HAFS V2, we are going, and one of the things which you would like to do for V2 is to introduce self-cycle DA. We had this capability in HWRF, and we were able to make better use of inner core vortex data using self-cycle DA. There are numerous papers by our HWRF partners, HFIP partners, as well as EMC, as well as for folks at AOML, especially Jason, who have looked at the impact of using these inner core data sets using self-cycle DA. So this is one of our targets for HAFS V2, which we hope to implement. Next slide, please. Now let's talk about some near-term and long-term plans. So, of course, DA does not live in isolation. DA has to pay attention to what's happening in the rest of the system, whether it's in the context of nesting configurations, physics, of course, as well as coupling. But just focusing on the DA aspects, some of the things which we want to work on, and it's essential that we get started on these things, is, we got introduced to a lot of new kind of observations. We need to start looking into ingesting those. And yes, there are challenges, and there are lots of steps to get them in real time. But still, in terms of our research and our ability to do testing, we need to start looking at those additional ops. Also, ocean DA, as reported by Hansuk, is coming along. And use of JEDI, which I'll get into a little bit more later, actually enables us to start looking into coupled DA for hurricanes. Another aspect of DA which we want to investigate, we did quite a bit of it in the last two upgrades of HWRF, was to actually see how we can do more with DA and less with engineering of VI, or vortex initialization. We want to be observations-based, science-based as much as possible, and use as less amount of engineering as we possibly can. Because engineering means you're making decisions a priori, which may or may not be correct. But if you're using DA, if you're using observations and DA techniques, then you know that at least you have a chance of reflecting what's actually happening in the real world. Big one, and I have this in red, is that we are making progress on using JEDI infrastructure for our ocean DA, as reported by Hansuk earlier. We made a lot of progress. Yes, there are other challenges which we need to look at in context of the quality analysis, quality control, and how do you deal with boundary conditions. So there are challenges, but still, thanks to a supplemental project, actually a couple of supplemental projects, and some work being done by our partners here at AOML, as well as Erasmus, we're making progress. And another one, which will be a topic of our discussion later today, and I'm sure will be part of Daryl's presentations, is start the transition from GSI to JEDI. Next slide, please. So in this context, again, the slide was presented briefly by Jing earlier today, Jing Cheng. And this is just one way where one possible transition path from GSI to JEDI, where the analysis using FCAT, 3D, and VAR, we can start with that and start converting that aspect of GSI to JEDI for use in HAFS. And on the right here is a kind of a tentative timeline as to how such a transition could occur, starting with simpler methods like 3D and VAR and using conventional OBS, and then slowly going into other OBS, inner core OBS, and introducing 4D and VAR and other methods which we have in place right now. But this is just one possible path. Next slide, please. So again, continuing with this, and I stole this slide from Darryl. So these are some of the key points which I would like us here in the HAFS development community to focus on in this context. So we need a JEDI transition plan for HAFS. This is because there will be no support to GSI in future. In fact, we are trying hard to freeze all GSI aspects as much as possible and encourage all our collaborators, not just in context of hurricanes, but all through UFS to move towards JEDI. And then as part of that, we need a schedule on which we can collectively work on. And in this plan, we need to define roles and responsibilities. EMC is just one partner. We need help from, thanks. We need help from everybody in making this happen. And Darryl will be talking more about this later today. So we need contributions from the community. We can leverage ongoing efforts from the global and other regional systems, namely GDAS and RDAS. RDAS is being built for RRFS. But of course, we have to focus on our needs here, our special needs which we need for HAFS. And along with this, there has to be, of course, a training plan. So we need to build in-house expertise at EMC in our core group of HAFS developers, as well as the core group of our partners, so that we can directly contribute using JEDI, just like what we do with GSI today. Next slide, please. A little bit about where we could be going in long term. So some of the things which we need to keep an eye on are observations, of course. I already talked about it. There'll be more observations coming. And both in the context of remotely sensed as well as in situ, there's tremendous amount of interest and tremendous amount of technology which is now being deployed to collect OBS. And we have to continuously refine our observation strategy along with it. AI ML methods for DA is also something which we are looking into other applications. Coupled DA, how strongly or weakly we couple, that's a separate question. But with JEDI, at least we have a chance, or actually the framework is such that it would give us a very good way of introducing coupled DA. All sky radiances and their methods, also other DA methods, and some of these will be discussed by speakers in this session, and along with DA physics interactions. Next slide. Once again, I'd like to just end with this slide and remind everybody as to where we are today and where we need to go. So whether it's DA developments, physics developments, any developments, this is our long-term objective, and we should be thinking about this as we forge our plans here for development of DA, perhaps. Thank you.
Okay. Thanks, Avichal. Okay, next we have Darryl giving a pair of talks. The first one is on global DA at EMC, and then the second one's on JEDI.
Yeah, just to make sure I can do 10 minutes each, so I have enough time. Thanks. So thanks for having me. This is actually my first time at the annual meeting. I'm thrilled to be here. I've been meaning to come for a long time. I've dabbled in data simulation for tropical cyclones through various parts of my career. So we already had a brief introduction to the current state of HAFS data this morning. So I'm giving back-to-back talks, and you let me chair a session, and you let me lead a discussion. So we'll see how this goes. I'm first going to give just a quick overview of various things that have happened in the GDAS and what we're planning in the near future. And I tried to tease out some things that I think will be of particular interest to the HAFS community. So leveraging things we're doing for the global that will be applicable to the hurricane problem. Next slide, please. So even though we're trying to quasi-freeze GSI, the observing system doesn't care. So we have to continually adapt and figure out how we're integrating assets into the operational systems, in particular investments from NOAA. So we just launched some satellites recently. We have to figure out how to assimilate data from NOAA 21. So these things keep happening, they don't stop. I have some backup slides. We had a major observation upgrade about a year ago. That's of particular relevance to the tropical cyclone problem because we expanded our all-sky microwave data simulation to include precipitation-affected radiances. This is a pretty significant leap in the data simulation community. We're not done yet. It has its flaws. We have some additional work coming as part of V17 to enhance this even further. But if you're interested, I have some details about this in the backup slides. Another interesting change has been the commercialization of the observing system. Some of this has been touched on within the context of UAS, but within NESDIS, there's now an entire commercial data program for which they're doing data buys, throwing stuff over the fence and saying, here, we bought this, use it. The example of this is the GNSS radio occultation data. Actually, we've been engaged with 3 different vendors now. The current purchase, I'll show sort of a time series of how this has gone. In some sense, this has been an interesting exercise because it's forced us to be agile and deal with sort of rolling, updating contracts with 6-month windows, and the observing system's now constantly changing. But I think it's also a little bit of a cautionary tale because in some sense, this is one of the easier problems for us to deal with from a global data simulation perspective from NWP. We know a lot about the observations. They're generally unbiased. We already have forward operators. We have decades of experience. It's pretty easy to integrate this type of observation into an operational system. That is not going to be true for a small sat microwave. It's not going to be true for other sets of unique observations coming away from the commercial sector. So we need to think hard, NOAA-wide about what this means for our concept of operations and how we're going to get this stuff into our operational systems. Next slide, please. So just some quick highlights. We just finally got the right version of CRTM updated into the operational supercomputer. We've done some early trials with NOAA 21 data. ATMS, so the microwave and CRIS, the infrared, these are just showing some examples. This is ATMS from NOAA 21 showing that O-B statistics look as expected, it checks out. We're going to turn this on operationally next month. Next slide. And here's some impact results. This is from CRIS, just showing it's only one sort of observing system. We are in the golden era of observations. It's really hard to move the needle on this kind of metric by throwing in one new platform. So this is, as expected, results are neutral to slightly positive. The unintended benefit of this, of course, is redundancy of the observing system. So CRIS on NPP, for example, has already experienced issues and we can't assimilate any longer. We don't know how long some of the other legacy instruments are going to stay flying. We're assimilating data that was supposed to have fallen out of the sky a decade ago. At some point, they are going to fall out of the sky. So making sure that we get the stuff into the system is really important from a risk reduction perspective. Next slide, please. And here's the same thing, but now the microwave, so ATMS again. Slightly positive results, in fact, slightly bigger than CRIS. This is a good sign. Microwave is sort of the gold standard for improving short-term forecast errors in the global system. Next slide. So I mentioned commercial GPSRO. Lydia's in the room. We're working very closely with her team and making sure that we keep up to what's happening with the commercial program in NESDIS. So this time series is all the operational changes we've made just in the last 3 years related to commercial GNSSRO. So they're rolling new delivery orders under contracts and changing vendors and changing aspects, deciding what kind of licensing they're going to use. We basically have to have someone on retainer now dealing with the constantly evolving set of changes that are coming from these rolling contracts, from these data buys. So as we figure out how we're going to integrate the commercialization, we have to figure out how this is going to be staffed and maintained. This is a fairly laborious sort of effort. Simulating observation is not easy. I don't have someone there to flip a switch. We have to do data checkouts, we have to do data monitoring, we have to do impact studies, we have to report back to Congress and how we're spending this money and what the impact is. This is a big effort on our part now, and something we weren't necessarily expecting even 5 years ago. Next slide, please. So looking to the future, Feng Lin already introduced what we're working towards for the next major upgrade to the global system. Of course, the big driver for this is going to be to implement a coupled UFS. We do have some assimilation upgrades planned as part of this upgrade to the GFS. The atmosphere is still going to be GSI based. This is in part because we are a little bit further behind on JEDI than we were hoping at this point. And because of that, we are going to try to sneak in a few last science upgrades as part of GSI, as part of this upgrade, one of which I'll talk about in a little bit. But for all of the non-atmospheric parts of the coupled DA system, we are implementing JEDI. So we have a fairly mature ocean and sea ice DA system under JEDI. We have a new snow assimilation system that is built on JEDI. We have an aerosol system built on JEDI. And we're starting to play around with strongly coupled land atmosphere assimilation using screen level temperatures to constrain soil moisture. Next slide, please. So I mentioned the all-sky work as part of V17. I realize no one can read a single font on this slide. That's not the point. This is here for reference. Going back, this is just showing some of the improvements we're making to the all-sky microwave. In particular, because part of V17, as Feng Lin mentioned, we're upgrading to the Thomson microphysics. So to be able to continue to use the all-sky microwave, we have to make some changes to the forward radiative transfer to be able to simulate that data. It includes things like a new optical lookup table so we get the scattering right consistent with the distributions in Thomson microphysics, along with some additional work in observation error and quality control. Next slide, please. Another thing that I think is particularly of interest to the hurricane community is we're finally making progress on the assimilation of microwave imager data. This is just a sort of list of stuff we've done with GPM, GMI. Don't worry about the details, don't worry about the scorecard, it looks neutral. But I think advancing and being able to use microwave imager data could be particularly interesting for the tropical cyclone initialization problem, in addition to the all-sky microwave work that we're already going to be able to leverage in HAFS. Next slide, please. And finally, the last kind of big science upgrade we're going to do in the atmospheric DA for using GSI is finally implementing a multi-scale approach. We've had a scale-dependent localization option available in the hybrid ENVAR for some years. At the time, we initially tabled it from V16 because we were trying to redirect resources to JEDI. Well, the schedule is what it is now, so we had this ready to go, so we're going to get it over the finish line. For years, we've actually had this. We've already done some work on this, using this in prototype versions of the RFS, including a variable-dependent localization option to improve radar assimilation. We had done lots of work in older versions of the global. Thank you. And I'm just going to quickly show you some results from GFS. Next slide, please. Some details. We ran lots of experiments. We're trying to mimic stuff that's already happening at the Met Office and Environment Canada, with various configurations of breaking up the ensemble perturbations into different wavebands. So try to make better use of the observations and basically doing a dual approach to try to constrain the large scales and small scales quasi-separately. On next slide. And similar to other centers, here's the scorecard looking at various metrics. This is root mean square error for an entire trial period, control and experiment, green is good. Scale-dependent localization improves our forecast skills significantly for many metrics. So this is going to be included for the atmospheric DA part of V17. Next slide, please. And hopefully that was only 10 minutes.
We're at about 9:45.
Nice. All right, so you're stuck listening to me again. Next talk.
Take a deep breath while we load.
All right, so Awachal stole a little bit of my thunder, but I'm going to use this a little bit as a teaser to what we're going to talk about in the breakout. So I'm just going to give a quick overview of status in terms of where we are in terms of JEDI development and integration at EMC. I'm not going to answer the question, when is JEDI ready, in this talk. That's the question I always get. I don't know when it's going to be ready. It's going to be ready when we make it ready. Next slide, please. So I already hinted that we have lots of work happening, not just in atmospheric DA, but in the other components for the weekly coupled system for V17. So JEDI is actually pretty mature for ocean, sea ice, aerosols, and snow, in part because we didn't have mature capabilities to beat. We were starting from scratch. we had either didn't have systems or we had systems that were quite old. So this was it was a little bit easier to accelerate this work. Replacing the atmospheric assimilation system in GDAS is a really high bar. We have a lot of work to do before we can get it over the finish line. So right now, actually this week, and part of the reasons I had to give the last talk is my team is busy doing a code sprint focused in particular on forward operator development and validation. So we're spending a lot of time on observation operators, quality control, observation air specification, everything we need to do to be able to use observation in the JEDI-based system for the atmosphere. We do have a very preliminary prototype of a cycling system for something that looks like the GDAS. We're largely just playing around with low resolution, 3D VAR, rudimentary background air, subset of observations, just to start turning the crank and rooting out all of the issues. And we're starting to build this out. This is going to be the capability that we're going to use. It's plugged directly into global workflow. So it's something that our development team is familiar with, and it still has a little bit of ways to go, but we're making progress, and I'll show some examples. And very recently, the RFS team has drafted a formal transition plan, and we have quite a bit of work that's begun on the regional convective scale specific task for JEDI, even while trying to complete version 1. So we're also trying to make a pretty hard pivot when it comes to the regional DA system. And this has not been without its own challenges, because like the HAFS DA team at EMC, the RFS DA team is quite small. So we have to make some hard choices about which resources go to what, so we can make sure that we plan for and execute the future. Next slide, please. All right, so here's my one slide version of this is when we're implementing JEDI for every application we have under the UFS. And you might notice there is no timeline along the top of this chart, which is intentional. But that's kind of by design, because one thing we've realized that rather than putting out some artificial milestone that we're going to implement JEDI by 2024, we need to define it sort of at the project level, work backwards to figure out what it's going to take to make it happen, and then fit a schedule that's going to meet the resources we put into it. So I've already mentioned the non-atmospheric parts of JEDI are going to be included in GFS V17. That is the last major upgrade of the GFS using GSI. V18 will complete the full transition to JEDI. I mentioned the RFS transition plan. RFS version 2, we are committed to implementing using JEDI. We don't know if it's going to be FE3 or MPAS. We'll see how this goes, but we do know it's going to be JEDI for DA. I have a box around HAFS V3, and I realize this hasn't really been discussed and committed to by the community. This is here as a placeholder, and one of the things I actually want to get out of a discussion while I'm here this week. It doesn't matter if it's V3, 4, 5, or 10, but we do need to make a commitment and start aligning the resources to make it happen. Next slide, please. So I already gave the list of what we're doing for JEDI for V17. So next slide, please. So on the marine side, I mentioned this is quite mature. We've had quite a lot of progress in addition to the regional marine DA work that Hansark's going to talk about. I'm going to give some examples from the global. On the algorithm side, we have a mature hybrid EMVAR capability. We're planning to implement 3D EMVAR with 4D HFX, that's FGAT. Right now, we only have an offline ensemble we're using to drive the hybrid, but we have already demonstrated the ocean LETKF that we're going to use inline to create the dynamic air covariances for the coupled system. We are going to run the ocean DA update as part of the early and late cycles, so the GFS and GDAS, for those of you familiar with the operational system. We just recently started testing IAU for MOM6. It actually seems to be working even better than expected, which is surprisingly good news. And we already have capabilities for UFO quality control and air specification for most satellite and in-situ observations. One thing we had done prior to this is we deployed a very low resolution, 1 degree, 40-year reanalysis, basically to turn the crank and see what we could get out and start solving some of the issues in the marine SOCA system. And that was the reanalysis. Maybe has some aspects of it that aren't perfect, but from a development perspective, it was incredibly valuable, and it set the stage for us moving forward. So in the pipeline, obviously the ensemble forecast for the coupled system, completion of the LETKF work so we can actually update the ensemble and create the dynamic air covariances. And right now we're using a lot of sort of pre-curated observations, so making sure we get over the finish line to connect directly to the operational data tanks. Next slide, please. So just some examples. The upper left basically shows time traces of comparisons of SST coming out of our weakly coupled system. So in this case, it's JEDI-SOCA for the ocean and sea ice, GSI for the atmosphere, comparing what comes out, just comparing our SST analysis to an independent analysis, in this case, OSTIA. And just looking at green, which is the operational, that's a benchmark, I think blue or one of these is GFS. Oh, sorry, the really bad one is actually our operational SST. So we have a lot of work to do. That's the one that is produced by the GFS. And basically just working your way down, we've had sequences of experiments. This is actually a really nice way of showing that we regenerate this plot every couple of months, and somehow the RMS keeps getting less and less, just sort of capturing the progress that we're making very rapidly on the development of this coupled system. And I keep joking that if we do this a year from now, maybe our RMS will be below 0. That's a joke. Mentioning the IAU, so looking at dynamic topography, just showing the result of recentering an IAU, we're getting pretty huge improvements in dynamic topography compared to an independent L4 product from Europe. Next slide, I think I have some, yep. So on the left is just a quick example. Details aren't important, demonstrating we have an aerosol 3D VAR system we're gonna use to initialize the GEFS aerosol control member. I mentioned the snow system, so we have a JEDI-based snow depth assimilation that we're gonna integrate as part of V17. This is showing the improvement in 2-meter temperature prediction by integrating the new snow analysis relative to what we do in operations now, which is just direct insertion using an offline analysis that we don't produce ourselves. Next slide, please. All right, so for those interested in how we plan to execute this, we just completed drafting our initial version of the transition plan for going from GSI to JEDI for the GDAS as part of V17 and V18. This just shows sort of the outline and the types of things we're focusing on. We're now taking this and turning it into an actual project with resource mapping and timelines, all of which is going to be publicly available, and figuring out sort of where the dependencies are on Joint Center core staff, partner contributions, et cetera. Next slide, please. So in addition, I mentioned this week we're doing a code sprint, but we're also trying to focus on not just the short term, so the basics. Single observation tests. Can we match performance of forward operator between GSI and UFO? Starting to build prototype cycling capabilities. So we're trying to do both at the same time to make sure we have the infrastructure in place when we're ready to go to do full demonstrations, while at the same time worrying about the nitty-gritty of everything we have to do in the short term. Next slide. So here's where we are in UFO acceptance. So if those of you have seen news articles or have heard some of the other centers, UFO is accepted. It's partially true. One thing that people maybe don't realize is a lot of the UFO acceptance work, other than what's happening at the Met Office, is still relying on GSI to produce intermediate files that go into JEDI. We are currently in the process of removing that dependency and going directly from the operational buffer data streams. So that's what the code sprint this week is focused on. So doing comparisons of end-to-end testing, going directly from the raw observations through IOTA, which is the format that's used in JEDI, to producing UFO, comparing it to the process of the same thing doing in GSI. Here's an example just last week. This is just from atmospheric motion vectors. I don't even know which is which, it's not important. There's literally dozens of GitHub issues and documentation about how this is going. I think we're about 50% done with the observation types. By the end of this week, it's going to be closer to 90%, including almost all the radiance data. So this has been a huge accomplishment, and this is the exact thing we need to build sort of operationally relevant prototypes of the end-to-end GDAS system. Next slide is just an example showing preliminary prototype cycling. In this case, it's just 3D VAR. We only assimilated for 10 days AMSUA NOAA 19 and conventional data. Analysis increments on the left, departures on the right. Obviously, when we have subset of data, we're not going to be as good. The forecast starts getting worse. But surprisingly, even just doing this, it didn't blow up. So we actually have something reasonable as a starting point for which we can now start doing scientific validation. Next slide, should be it. Oh, last thing. Similar to the GDAS transition plan, the RFS transition plan has just been completed within the past couple of weeks. This will also become publicly available soon. Just showing the focus areas. This is also being turned into a formal project with resource mapping. So I'm specifically mentioning these transition plans in a talk. I realize it's boring, But one thing I want to get the community focused on is building a transition plan for JEDI for HAFS. And these documents can be leveraged and should be leveraged. My team is happy to contribute, and we're going to get there. And I think that's it. So now we'll hear all about RFS from Curtis. Curtis, are you online?
Yeah, can you hear me?
Yep, very good. You have 10 minutes. Go away.
All right.
ahead.
Thanks, Daryl, and thanks again for the opportunity to briefly go over where we're at with the Rapid Refresh Forecast System V1 data simulation. I want to give credit, of course, to Jacob Carley, collaborator at EMC, for all the work to get us to this point, along with our other EMC, GSL, NSSL, and other community staff. So just a lot of collaborative effort here to move us toward a first operational implementation of the RFS. So next slide. And this just pivoting off of what Daryl showed a little earlier, the focus here, of course, is consolidating and reducing the number of regional modeling systems and operations, with the RFS subsuming quite a few of those. So the first target here with RFS V1, of course, is what I'll try to talk about here over the next couple of minutes. So next slide, just emphasizing V1. Yep. Next slide. So for those that aren't familiar, I think at this point, most probably are. We have this FE3 based RFS that's going to be hourly updated, 3 kilometer grid spacing over all of North America, 65 vertical levels, and a hybrid 3D and VAR data simulation. And I'll talk more about that in a minute, along with some additional physics enhancements that will include smoke and dust treatment. We've been making forecasts to 18 hours every hour, ensemble forecasts, and singular deterministic forecasts to 60 hours once every 6 hours. Next slide. So again, this is a big domain, a lot of computational cost for this, but it's going to give very high resolution information over all of North America. You can just step through this sequence. So obviously you can see fine scale convective details as you zoom in to the county scale. And then obviously this is part and parcel of what we want to provide for forecast guidance from the RFS in terms of weather hazard threats across seasons. Next slide. Physics suite for this is certainly familiar for what we've been using in the past with the RAP-HER, but obviously development has taken place in all of these parameterization schemes. Just to note, we're including now a variant of the Grell-Freitas deep convection in our most recent RFS testing at 3 kilometers, as well as using the CLM Lake model, FECOM for the Great Lake water conditions. And again, we talked about the vertical structure on a prior slide. So I'll move on to the next slide. We are including, again, the planned effects of smoke and dust into the forecasts like we had with the RAP-HER system. We'll have this in the RFS. This is an example of the smoke forecasts from this past summer with the Canadian wildfires contributing to quite a bit of that smoke over the US. We're leveraging satellite information for initializing locations of wildfires, and then again having the model physics handle the ensuing evolution of the PM 2.5 into the atmosphere. And we can compare that against observations again, and shown at lower left here, the RAVE compared to the RFS forecast of PM 2.5. So this is a capability we will have for the RFS V1. Next slide. In terms of data simulation, which I will spend the rest of this presentation focused on, we are doing a partial cycled spin up, both for the ensemble as well as the controlled deterministic member. And so this is going to entail 6 hour, twice per day spin up from GDAS perturbations that will carry forward into the control. That'll use a hybrid E and VAR for the analysis. Again, we'll be leveraging 30 regional CAM ensemble members as part of that DA system. And so then that system will cycle hourly with those 30 regional members around the clock. We're using ENKF, and again, these perturbations are going to be reinitialized from the global GDAS twice per day. Next slide. So graphically depicting that, you see the 30. It's going to be 30 members. So compute resources are dictating that, obviously, for cycling throughout the 24-hour period in an ENKF infrastructure. Again, we'll be partially cycling or reinitializing those perturbations twice per day from GDAS. And then that's feeding into the ENVAR controlled deterministic forecast, which is the middle row of arrows there. And then those deterministic forecasts are also going to be partial cycled from the GFS atmospheric state twice per day. The motivation here is to bring in the larger scale information, also the latent observations that come from the larger scale information into these regionally hourly cycled configurations. So we have this set up here, and we are going to feed back from the control to the ensemble, recentering twice per day to give us that two-way interactivity that we didn't have with the prior HER ensemble DA system. And so that's really a highlight there. And I think you see the obs at right that we are working on to assimilate in this DA infrastructure from radiances, aircraft, lightning, radar data, rainwind SON, and other conventional observations. Next slide. And so one of the changes we made recently is to move from GEFS to GDAS for the starting point of the perturbations that, again, feed into the 30-member regional ensemble. This really helped reduce the surface pressure tendency metric for noise in the model forecasts from the GDAS perturbations. The motivation for the GEFS data use was to try to bring more spread into the regional ensemble. But it turns out that in the end, we didn't really see the impacts of that in the standard verification metrics. So the GDAS perturbation structures were certainly giving us better forecasts and less noise when you look at the deterministic measures, sensible weather verification. Next slide. We are also focused on surface data assimilation and other improvements in terms of surface boundary condition mapping and handling of higher resolution soil state data. We'll be using real-time satellite greenness vegetative fraction to update that part of the land surface state. We're using the FECOM for the Great Lakes treatment of surface temperature and ice coverage. We are doing the moderately coupled land data simulation. We're adjusting soil temperature and moisture based on low-level atmospheric analysis increments as we had done with the RAP and the HER, and some of the other types of treatment for observations in complex terrain to handle the terrain and model height differences. So there's just a few highlights here from what we're doing on the surface DA front. Next slide. And again, the moderately coupled DA certainly helps us improving the low-level atmospheric forecasts, both in terms of error and reduced model bias. So we see that as a compelling benefit to having that in place for RFS V1. Next slide. We're also assimilating in radar reflectivity. We have the reflectivity as a control variable. Again, this is leveraging some OU map work, contributing to the radar DA, both in the ENKF ensemble as well as in the EN bar for the control analysis. We're seeing improvements in some aspects, but also some challenges here where the DA had been producing a high bias in the short-term forecasts of reflectivity for convection and precipitating processes in the model. And this was validated in the spring forecast experiment. You see that in the performance diagram at right. The bias for the RFS forecast is higher than the compared control forecasts from the HER as the operational baseline. So we made some changes to the use of the radar reflectivity data on the next slide. And that basically drove thinning of data, reduction in use of radar reflectivity observations that helped us reduce the noise in the forecast. So that lowered the bias, improved the forecasts. Next slide. The only other thing I'll highlight here is we'll be assimilating GLM lightning observations. Right now, we're just testing the impacts, covariances across grapple, vertical velocity, and rain, and then it's producing expected results, taking GLM flash extent density and mapping that to those forecast variables. Next slide. Bringing in radiance assimilation up to the new higher model top compared to the RAP and the HER. This is all clear sky only assimilation at this point. Next slide. But we are seeing the impact of the radiance assimilation when we do data denials. It's certainly one of the more significant contributors, at least in the mid-troposphere, to reducing forecast error. Next slide. And so the remaining items we're working on, again, getting all the GLM lightning DA installed. We're also looking at scale-dependent localization as well as some large-scale blending. Next slide. Which I will say, we're sort of the final testing here to bring in the ability to modulate the covariance length scales for localization, reducing the noise in the model analyses when we do that. and into the ensuing forecasts. So that's showing a promise as well to be able to bring in this multi-scale DA capability for the first time. Next slide. And then the blending, which is also another way to preserve multiple scales of information from the perturbations, not only from GDAS, but the cycled 30-kilometer regional ensembles. So we will be potentially blending the information across those scales as we restart the perturbations again in that partial cycle spin up 2 times per day. So I think that's my last slide. And yep, in the summary, big change coming with the RFS, replacing a lot of regional modeling systems. We're going to start a beta evaluation now, basically, with the soft freeze of the RFS here at the beginning of December. Hard freeze is slated for the end of March if the beta evaluation is successful, and then we'll go into the formal science evaluation beginning in April, with a targeted operational implementation Q2 of FY25. So I'll stop there if there's time for questions. If not, I look forward to the discussion later. Thanks.
Thank you, Curtis. Yeah, we're going to defer questions to later. So our next speaker will be John Potterjoy.
That's better, right? All right, thank you. So next slide, please. Yeah, so my talk is going to focus on, oh, the animations are not working. Yeah, so my talk is going to focus on a lot of the work that's going on in my research group that focuses on bringing fully ensemble data simulation to a version of HAFS that runs nonstop ensemble DA over large areas. This is supposed to be an animation of just visible satellite imagery coming from analyses every 6 hours. If you click on it, does it run? Maybe not. Okay, that's not going to be good for the rest of my talk then.
You want us to try to reload it?
Actually, yeah, could you bring it back up? Because some of my results are actually coming in the videos. So if you load it in Acrobat instead of, yeah, you have to bring it in Acrobat. Yeah. I'll keep on talking. Yeah, so our developments actually focus on treatment of sampling deficiency and ensemble statistics that are needed for making this happen over large areas, as well as dealing with non-Gaussianity, the statistics that go into data simulation. And what I'm going to do for my talk actually is take a step back and give a less of a DA operational, oriented talk and more of one that's for everybody in the room, including forecasters, to better understand what's going on during data simulation. And point out some of the deficiencies just from a example that Jason Sippel actually pointed out in one of his talks yesterday. Here we go. Is it not now? There we go. Do you do like full screen and I think it should be okay.
Where is it on? Sorry, John.
Oh, just go to geez, I'm a Mac user.
Yeah, that's my problem too.
Yeah.
So am I. Is it?
Here we go, and it should work. Yeah, okay, excellent. So you can go to
Thank you for bearing.
yeah. All right, thank you. If you go to the next slide, please.
I'm gonna restart
Yeah.
in 10 minutes, by the way.
All right, thank you. And yeah, so I'm actually going to focus on Hurricane Lee, which was already looked at a lot yesterday. And so I'm borrowing screenshots that Jason Sippel sent to me a few weeks ago. He was vigilant enough to keep them during the season. And so I'm going to focus on a cycle that we had notoriously poor intensity forecasts for both HAFS A and HAFS B, and discuss reasons why DA played a role. And so we go to the next slide, please. So just to zoom in on this is a 6-hour forecast, just showing MSLP and wind speed contours, and for HAFS A at this time. And I'm going to talk through what the DA system actually does operationally, starting from this first guess. So next slide. So for this specific cycle, we actually had really good observation coverage. And so there's a lot of really excellent talks. The previous session talking about new observing capabilities. Here's a situation where we have extensive, like horizontal coverage in the OBS. Next slide. The analysis was awful. And so we had major unphysical asymmetries in the vortex that looked almost like you had ghost storms, coming from maybe like artifacts in the first guess field. And so if you go to the next slide, let's discuss how that works. And so the idea behind data simulation is for the variational DA system we're using for HAFS is the idea is to come up with this increment that we're going to add to our first guess field in order to get to that analysis. Next slide. That increment just comes from a weighted combination of perturbations that are coming from an ensemble. And so in this case, our ensemble comes from GFS. And so we actually are going to take perturbations that GFS, weight them to give us that increment that I showed you. Next slide, please. So that XF is just our first guess. This includes vortex relocation as well. Those A's are our control variables. That's what the variational DA system is going to find, whether it's 3D ensemble var or 4D ensemble var. And those X prime values are just coming from our 80-member GFS ensemble that's used for GDAS. Next slide, please. And so we have two very important assumptions. There's actually more assumptions than this, but I'm just going to focus on two of them. One is that our error in our XF is modeled using a Gaussian. The second is the error covariance for that Gaussian is perfectly prescribed from a sample estimate given by our XN primes. And those XN primes just happen to come from a different model in this case, so they're completely divorced from the XF. Next slide, please. What I'm going to do is run through a bunch of experiments I actually ran on my laptop on my way here to this meeting, in which I just reproduced this problem using a very simple two-dimensional wind field. And so here I just took a 2D axisymmetric wind field that I generated from a ranking vortex profile. The parameters that describe this wind field are just the radius of max winds, Vmax, and essential position. And I'm going to call this my truth. And from there, next slide, please. I can generate some synthetic observations, which I'm just going to mimic what we do for TDR, and have some radial wind observations that I'm going to assimilate back into this problem. And so those are the distribution of my measurements. Next slide. Prescribe a background. In this case, I'm going to assume that we did vortex relocation. It was done perfectly, which of course is never really the case, but in this case, I can just assume it was done perfectly. And that's what the background looks like. It has an error associated with the peak winds and Rmax, which has to be corrected by data simulation. Next slide, please. And then I have to give it an ensemble because the weighted ensemble perturbations are going to define what that increment is. And so I just provided some ensemble that has uncertainty in Vmax, Rmax, and the position. Next slide, please. And I did a series of experiments, two of which give me major asymmetries. And here, what I'm showing you is a set of animations where I induce some mismatch between XF and XN. On the left, I have a perfectly like relocated storm for XF, but then for XN, I give it a southwest bias, and so I separate it from what the first guess has. On the right, I keep the ensemble centered on the true storm, but I pull the first guess down to the southwest quadrant, and the dashed line just shows you the true Rmax that we're trying to get to. Go to the next slide, please. On the right, I'm just showing you the end result if I have a displacement error that's comparable to what we saw for the cycle of interest. And I want to note that on the right, we can correct this problem using vortex relocation. You essentially have this artifact in the bottom part of the domain. The DA can't move the full storm to its right place. On the left, you have a similar looking artifact that's actually coming from the GFS ensemble. And we don't have control over that, when we don't do our own self-cycle data simulation. And also on the left, I just added an extra case in which I have some structure bias. I gave my experiment just a set of perturbations coming from an ensemble that had broader, weaker vortices, similar to what we'd have for GFS. That also induces some type of bias as well. But the two important ones are the ones on the right. Go to the next slide, please. Now, if I remove the mismatch between XF and my ensemble, the way you do that is you just give it an ensemble mean first guess, and so you have accurate statistics that are being used for DA, but you don't remove the problem. The reason being is it's a very non-Gaussian DA problem. it's actually been explored to death by a number of papers. The challenge of doing data simulation for displaced vortices for a geophysical model. Now, before you go and play games with relocation for the ensemble, if you go to the next slide, please, I want to point out that this is actually a major problem across all scales when we do data simulation in the atmosphere. On the far left, I'm showing the output of ensemble common filter, just one member, through cycled DA in one of our experiments that we ran in the UMD research HAFS formulation. And on the right, I'm showing an example of just one member from a completely non-Gaussian DA method that we've developed in our group that's based on particle filters. And you can see on the left, all that noise that you see in the vorticity field, which I'm showing in these videos, is essentially exactly what you see in that vortex example that I showed before with those asymmetries. The DA assumptions that are going into that example are actually inducing, some unphysical behavior in our initial conditions that are usually taken care of by a variety of the acronyms that you saw in some of the previous talks, such as IAU or digital filter initialization, other methods. And so this is an issue that exists across all scales in our model when we do data simulation, not just the TC vortex. And so it's a really fundamental limitation of what we have unless we move towards a more non-Gaussian method. If you go to the next slide, please. Now, if I were to take the ensembles that were generated from our self-cycled ensemble system and plug them into a DA system that resembles what we have for HAFS and extend that DA system over the whole domain instead of just over the nets, you could do some comparisons of what we leave off the table also when we don't do self-cycled data simulation. And so the green line is showing forecast RMSEs for a bunch of variables, temperature, wind, specific humidity, absolute vorticity, averaged over our whole domain. And the green line is showing the results if we were to feed in the GFS into a variational DA system over that area. And the blue and red lines are showing the results if you were to feed in either an ENKF ensemble or particle filter ensemble. Particle filter ensemble is marginally better than the ENKF ensemble, but both of these experiments are miles better than just using the GFS. That provides some motivation to some of the earlier talks to emphasize more self-contained ensemble DA system for HAFS. Next slide, please. Now, I wouldn't be a good DA scientist if I didn't make problems like this go away. And so what I'm going to do next is I'm going to also just provide a pitch for an idea that I have for bringing in some of the mathematics that go into that particle filter into the variational DA system. So go to the next slide, please. In this case, what I did was I reformulated E and var to actually remap those ensemble perturbations that we read in based on a preliminary DA step to remove some of the non-Gaussian behavior. And you can actually, if you can't afford to run a fully cycled ensemble DA system, you can still make some of these artifacts go away if you were to just do a clever use of assumptions for the background errors in the bar cost function as well. And so I just wanted to throw that out there as another research direction for EMC. And one nice aspect of this is it removes the need for vortex relocation. Next slide. Quick summary, UMD is currently testing multiple self-cycled configurations of HAFS, thanks partly due to the NOAA JTTI program. Motivation is self-consistent ensemble statistics for Hurricane DA are very important. There's a paper outlining this. Non-Gaussian ensemble data simulation developments have reached a level of maturity where they can be used for really big modeling problems like this. And one thing I didn't touch on was a lot of the issues for simulating satellite radiance DA that we have for HAFS really do require a self-cycled framework. And there's another paper here coming from my group on that topic as well. Thank you.
Thank you, John.
John, I want to give you kudos. You only went 7.5 seconds over. That's pretty damn good, considering our rough start.
All right, our next speaker from OU, Shuguang Wang. Shuguang, you online?
Yes, can you hear me?
Yep, 15 minutes. Take it away.
Is this full screen?
Yes, it is.
Oh. I can't see the bottom part of my slide
Hold on.
for some reason. Okay, there you go. Much better. Okay, so my name is Xuguang Wang. I am working with a group of students and scientists, multi-scale data simulation predictability problems at University of Oklahoma. And so I'll be sharing our recent research development RTO efforts for HAFS data simulation by our OU Map Lab. So this is we are enjoying the collaboration with multiple EMC and AOML colleagues. Okay, next, please. Okay, I'll briefly mention this RTO efforts. Avatar actually talked about this already. So our OU Map Lab actually collaborated with EMC and helped implement the 4D envar in HAFS, and EMC conduct this pre-implementation tests comparing 4D envar and 3D envar and found improvements for both track and intensity. So this 4D envar became operational through HAFS version 1 beginning summer this year. Next, please. So in the rest of the talk, I'll be sharing our recent research development for HAFS DA. I will talk about 3 topics. The first one is a simultaneous multi-scale data simulation of HAFS 4D envar. The second one is the development research goes ABI all-sky radiance data simulation for HAFS. And the third one is about efforts toward the eventual HAFS coupled data simulation. And here we are focusing on improving the background ensemble at the RC interface. Next slide, please. So Daryl actually talked about this multi-scale data simulation in his talk already. So in this topic 1, in our earlier studies, we found that the simultaneous multi-scale data simulation compared to a sequential approach can allow all observations to be used to correct all resolve skills all at once in a coherent fashion. Next, please. So both Daryl and Curtis mentioned the efforts of implementing and testing the SDL, the multi-scale data simulation, using SDL for GFS and RFS through collaborations between EMC, GSL, and our group. And here I'm talking about the efforts we made recently to extend the simultaneous MDA with skill-dependent localization for HAFS. Here I'm using 2 observations as an example to illustrate what MDA does. And as you can see from the middle column, and multi-scale data simulation with SDL can simultaneously correct both the TC vortex and also its large-scale environment. If we are using a single small-scale localization, 4DS here, you'll see that the correction made to the large-scale environment is too limited, too constrained. If we use a single large-scale localization, an experiment named 4DL, you'll see it's doing a fine job for correcting a large-scale environment. However, it's also showing sparse corrections near the TC vortex. Next, please. So we used Hurricane Laura as a test bed for this simultaneous multi-scale data simulation. And as you can see, the multi-scale DA in red for the SDL is improving upon the 4DS, which is single small-scale localization in green for both intensity and track forecasts. And for when the SDL is compared with the 4DL, which is single large-scale localization, it improved the intensity forecast. It shows comparable track forecasts. Next. The question is why, right? So we actually done a few diagnostics in the interest of time. I'm only going to show 3 examples. So we first try to verify the 6-hour background forecast against various in situ observations that are different scales. For example, drop sound sampling vortex, and radio sound, AMV wind, sampling environment. So what we found is that MDA is able to produce better background forecasts and the single scale localization in both vortex scales and also environment. Next, please. We also look at a case study to understand why the track is improved over the 4DS approach. Basically, for this particular example, we found MDA is able to improve the large-scale environment. Here, specifically, it is the extent of the southwest edge of the Atlantic subtropical high. This turns out to be important to steer the hurricane track towards the best track. Next, please. So why is it improving the intensity prediction as well? So from diagnostics, and we found the analysis using the multi-scale data simulation with STL is able to produce a stronger warm core analysis. This will affect the subsequent intensification forecasts for Hurricane Laura. Next, please. Okay, this is second topic, efforts on GOES ABI all-sky radiance data simulation. And so far the conference has a lot of talks on aircraft observations, and we indeed found in our past study that if we use advanced data simulation methods and simulate those observations, it indeed can show improvements for hurricane predictions. However, aircraft observations are limited by space and time. In the meantime, we know hurricanes spend like a lot of their time over the open water, and the satellite actually played an important role sampling the hurricanes over the open water. So our goal here is to develop and optimize GOES ABI all-sky radiance data simulation, or HAFS, and try to study its impact. Next, please. So in the next few slides, I'll share the implementations we made in order to enable HAFS ABI all-sky radiance simulation. The first development is to implement hydromedia update. HAFS does not update the hydromedias yet, so we have to implement the hydromedia update. Before we do that, you can see the observation priors does not see the hurricanes or clouds at all. After implementation, observation priors are now able to see the clouds and hurricanes. And this also allows us to do the hydromedia update as well during the data simulation. Next, please. So we also implement this all-sky radiance adaptive bias correction approach and the adaptive observation error estimation approach for the ABI. The basic idea here is that the bias is calculated as a function of a symmetric cloud effect, and the observation errors are also estimated adaptively as well. Next, please. So we use LoRa to test this GOES ABI all-sky radiance simulation. We actually use this self-cycled, self-consistent dual resolution 3D environment using HAFS' own ensemble at 6 kilometers and the control environment at 3 kilometers. As Jing mentioned earlier, it's kind of co-developed between EMC, OU, and other partners. And it was similar, all observations include, and also the GOES ABI channel 10. We use the adaptive thinning approach to pre-process ABI. This is also work we leverage from other members of our group. Next, please. So, so this is Hurricane Laura results. The blue line is the experiment simulating the all-sky ABI radiance observations with the bias correction and observation error estimation approaches that I just introduced. And the red curve is not simulating ABI observations. So as you see, after this bias correction and observation error estimation, simulating ABI is able to improve both the track and intensive forecast for Laura. And due to time limit, I'm not able to show the specific diagnostics for why. Just to summarize here, we found the improvement is coming from both the environment analysis improvement and the inner core analysis improvement as well. Next, please. Okay, so vortex relocation was mentioned a few times. If it was implemented correctly, it can help improve background forecast accuracy and therefore improve analysis. As John also mentioned, it can also alleviate the non-Gaussian entity in the background ensemble when the vortexes ensemble have like a large deviation from the truth. So, but the previous vortex localization from EMC does not have the capability to relocate the hydromedias. But for cloudy recent DA, we need to relocate hydromedia as well because we're updating hydromedias. So we're working on integrating the hydromedia-enabled vortex relocation that is developed by EMC to the all-sky radiance DA workflow. And we're still working on it, but so far the VR component seems to be working reasonable, but we need to test that in the DA cycling mode as well. Next, please. This is my last topic, efforts toward HAFS coupled ocean atmosphere DA. And the current DA practices tend to treat the ocean DA and atmospheric DA separately. It will cause inconsistencies at the air-sea interface. So there are many challenges to actually achieve the eventual coupled DA for HAFS. This study focuses on addressing how to improve the background ensemble at the air-sea interface first. Next, please. So we began with Hurricane Fiona, and we ran this self-consistent self-cycled HAFS dual resident EMR. We name this as CTL in the next few slides. We first start with HICOM ocean model, and which I will show, and we're working with MOP6 as well. So for FIUNA, we can leverage a range of inner core observations for both the ocean atmosphere from the field campaign to verify the background and the background ensemble at the air-sea interface. Next, please. So this is an example of the air-sea interface observations from sail drones, and you can see a time series from sail drone 1031, 1040. This provides very interesting data sets for the verification of our background ensemble. Next, please. Okay, I'll first show how we verify our 6-hour background ensemble against sail drone observations. And so the dark blue and the green are the sail drone SST and the near sea surface air temperature SAT. The other 2 curves are from the models. Depending on which sail drone you're looking at, in general, SST is verified better than SAT. And and they both actually have low bias compared to the observations. Next, please. And we also look at other variables from sail drone like Q, PS, UV, and we found in general model, the pattern is following the observed pattern pretty well, especially for pressure. But for Q, you tend to have like low bias, and for wind speed, you tend to have high bias. Next, please. And we also try to leverage drop sounds to verify the boundary layer structure from the HAFS. And this is azimuthal verification as a function of the radius maximum wind. And black is observation. The blue is our control run, our run. And you can see our self-cycle DA is matching the drop sounds reasonably well, in my opinion, although it's smoother compared to observations. Has actually is performing slightly worse than our model, actually, in this case. Next, please. So we also leverage the paired drop sounds XBT because it allows us to see the profiles of temperature from atmosphere to the ocean. So what's showing here is basically temperature profiles from the atmosphere to ocean at the about 1 radius maximum wind. So this average about all drop sound pair AXBT pairs on the left. So overall model is capturing the profiles well, but you also observe the low bias for both atmosphere and ocean. Next, please. So as I mentioned earlier, the background ensemble quality really matters, in terms of whether we're going to be successful for coupled data simulation. So we also verify the ensemble as well, which is in red curves here. So this sail drone 1031 pressure, I think is doing well. For other variables where we observe model bias, you can see observation is falling outside the envelope, okay, of the ensembles. So what does this mean? It's saying we need to improve the background ensemble sampling, or we need to improve or reduce model bias at air-sea interface in order to do a good job for coupled ensemble data simulation. Next, please. I will do the same thing for drop sounds, and this is whole profile in the first row, and this is at the boundary layer, azimuthal verification. You actually see a model is doing not bad, actually pretty well in terms of capturing the structure, but you do observe the green curve, which is observation, is outside the envelope of the red curve, which is ensemble, suggesting the need of improving ensemble sampling and reduce model bias. Next, please. Okay, this is my summary. I'm not sure how many minutes I have left, but I want to emphasize the ongoing work for simultaneous multi-scale data simulation. We have a discussion with Jing Chen and Jen Zhang to talk about further test data in the HAFS 14 VAR context. For GOES ABI all-sky radiance DA, we are going to further optimize the all-sky radiance DA, start with looking into the impact of hydromedia enabled VR, and looking to further improve the bias correction observing error estimation methods. Next, please. For the efforts toward coupled data simulation, so we are in collaboration with LML and HRD and Hansuk and Jun Zhang, we are trying to implement a model state physics perturbation to further improve the sampling of the background ensemble at the RC interface. We'll look into the impact that for weakly coupled DA first. We're also working with Hansuk, Yunzuo, and Hisuk to further evaluate MAM6 HAFS configuration. And so we start with weakly coupled DA, but we eventually would like to start some initial trial of strongly coupled DA. Start with something simple like updating SST by using the atmospheric in situ observations. Next, please. Okay, I think this is my last slide. This is just showing the publications that I are cited here. Mostly are done by students and early career scientists in my group. Thank you. Oh, okay. I don't have to show the slide.
Thank you, Xu Guang. All right, so we'll move on to our last speaker in this block, Hansuk Kim.
All right, don't hate me. It's been third time on the podium today.
We have
Okay.
to move the slides for you because the
Yes.
thing's broken.
Okay,
you got
so-
10 minutes.
Thank you. Okay. It wasn't 15 minutes of time.
No,
Okay.
it was.
Why you've been changing it? And
No.
the 5 minutes is a long time
no,
for me.
There
Okay.
was 15 minutes to Avichal and 15 minutes to Xu Guang. Everyone else was 10.
No, it wasn't. Anyway, so this project is supported in part to JTTI to work with the Shugang, which you saw earlier, and the second one is coming from the UXX project for concurrent co-located Cedron and then glider observations. Next. So you saw this MAM6 system with the HAFS, and then click. And then that is the Marine Jedi MAM6 system that we are planning to do. So in the box for the Marine Jedi MAM6 analysis, obviously we have number of choices coming from the Jedi. So currently we are working with the 3D bar for now. Next. I'm going to skip this one. And then this is a sensitivity to background errors. So we happen to have two types of background errors coming from the global 1/4 degree in 75 layer MAM6 ensemble forced by GEFS. We call the STD55. And the second one is more than 10 years simulations with 112 degree and then 75 hybrid global MAM6. That is called the GMAM6. That is forced by JRLA 55, done by GFDL and the FSU group together. Okay, so we did a test with the background error, and then it found that there is no differences, or little differences in SST and then SSH analysis. Let me speak because of lots of data is coming from the the remote sensing observations. So it's hard to change any differences, but we do have some notable differences in the surface salinity SSS observations and the subsurface T and S values. So for SSS simulations, obviously STD55 analysis, it's a little bit better performed than global MAM6. And then the figure on the right shows that subsurface temperature stats for analysis in darker red for RMSE and the bias in the blue. And then the background, observation minus background is in orange for RMSE, and then the bias is in, I'm sorry, I flipped it. So blue, and then analysis bias is in green for with the STD55 upper panel and with the GMAM6 and the lower panel. So I didn't put a number on it, but in general, with the STD55 seems to performing better. If you look at the only green lines in the both figures, and then it seems to be performing better with the STD. Next. And then this is the one example of the observation coverage for Hurricane Fiona in August 20th. So top left is absolute dynamic height tracks, and the right one is sea surface salinity swath, and the middle panels, 4 panels shows that the remote sensing of sea surface temperature coming from different platforms, and the bottom 2 panels shows that temperature and in situ observations for this particular period. So as you notice that in situ observations, it's just a tiny fraction of remote sensing observations. And then worst part is, SST remote sensing observation doesn't cover, storm locations, which is pretty much blank at the, L-shape side of the L-shaped area of the best track there. Okay, so we happen to have, luckily, gliders observations in that particular locations. But if there is no glider or other in situ observations, we pretty much doomed out. Okay, because SST is not going to do well on this particular TC area. So we have to rely on ADT, which is top left, and then using the coupon hands vertical projections, and then we have to check with the balance, through the in order to get the TNS profiles correctly. Okay, next. Okay, so this is we've been running the Marine Jedi for 2020 and the 2022. This is one of the example that we do comes from the daily analysis for Hurricane Fiona. And then we also compare this one is independent L4 OSTIA SST observations, and the left 4 panels shows that all correlations, standard deviation, RMSV, and then bias against the OSTIA observations of model analysis, daily analysis. Okay, and then the color figures on the right side, those are the MAM6 analysis on the left, and the OSTIA analysis product on the B, and then third one is the differences. So for the pre-PI, apparently we do, rain is weak, so you don't see much differences, except that around the circle area they had to have more positive differences through the analysis compared to independent products. But during the RI period, the difference is quite large. It's pretty much large positive and the large negative, staying next to each other. So okay, so we can say partially it comes from SST cooling, but this validation, independent validation, might have to do with the data we are ingesting, or lack of observations. Next. And then we do currently working on improving correlation length scale, not only horizontal but also vertically. And the top 2 panels on the left, we do showing different increment, SSS increments, and using SOCA error covariances on the top and then Sabre on the bottom. Okay, so you guys notice that in the Sabre, it is just pixel. It's a lot of increments. It's only pixel size. Okay, so what's going on? And then we do the experiment through the SOCA bump 3D using either set correlation length scale coming from the another separate name list on the top, and then we have a fixed 2 experiments done with a fixed horizontal radar scale with a 250 kilometer in the middle and then 550 kilometer at the bottom. So just pay attention to dashed circles over there where the storm comes in and where the glider observations existing. And depending on the horizontal length scales, we do have a quite different analysis field. This is the SST field, right? So, okay, so we need to improve this correlation length scale. Next. And then this is one example that the Youngju has done at the EMC. He set it up workflow and then integrated the MUM6, Marine Jedi MUM6 to HAFS system, and then he has done the test with the 6-hourly analysis. In this case, this is Hurricane Lee, and the 3D analysis on the top right, austere on the right, and the no data simulation in the bottom left corner, and then the line plot showing the RMS E at the top, and then the bias at the bottom with without the data simulation. So when you look at the red, which is the data simulation, obviously reduces the negative bias of the MUM6, but look at the over 5 days period, the trend is quite larger than without the data simulation. So that means we need to I think a different way to apply the data simulation. So next. Okay, so okay, almost done. So this is I'm looking at the same simulations, but it's a Hurricane Fiona case. Again, this is 6-hour analysis. We are looking at the different water temperature at the different levels, and from left to right, it goes down to deep, and then consecutive cycles from bottom to up. So you see there are cold spots and hot spots near the Puerto Rico. That is coming from the glider observations. Impact on the glider observations. It has to do with the length scales. So okay, so let's. I have to. This is the homework that I have to solve it. Next. So concluding remarks. Okay, so MUM6, it appears to have a little bit moderate bias, especially for SSD and then even subsurface temperature. It appears to have a negative bias. So, but in the meantime, we have to improve on MUM6 modeling skill. And then as for 3D in the Marine Jedi, we have to decide, choose what's the best covariance model we are working with the correlation length scale only for not only horizontal but vertically, to better value of the ADT comprehensive approach. In other words, we have to check the balance of throughout the water column. And then thirdly, analysis windows. So again, 6-hourly window, if you use remote sensing observations, it's doable. But with in situ observations, if you want to correct the subsurface temperature and the salinity, we need to think about again. Okay. So merging Marine Jedi workflow with the MUM6 HAFS system, we need to redesign it in order to better control the input parameters. So I have to propose in the work session with the EMC about this workflow. And the challenges so far, we've been struggling with the spec stack, continue changing it. It's a moving target. And then 1 week it worked fine. The following week, oh my God, it's broken down. Okay, there is no warning system. There is no way we can know until we ask them around. It happened 3 weeks ago. Daryl. I know you didn't do it, but we have to coordinate well with the EPIC and the EMC all together. Okay, so we cannot play separately. Okay, and then future plan. Conduct the background error. We have ensemble MUM6 high resolution output available in order to provide the error covariance for Shugang's plan. So we want to use this one, sort of expecting better analysis because we are using consistent background errors. So next one is again correlation length scale and the data analysis windows. And then once you are content with the data simulation, we're going to go with the data impact study, especially focus on sail drone and the glider observations. And then finally, we wanna find a better perturbation method for ENKF or ENVAR for later on. Thank you.